So from this point through the end of the semester, we're going to be doing inferential statistics pretty much all the time. We'll cover a little bit more research design stuff, but just kind of get your mind in the mode of inferential statistics for the rest of the semester. Lots of stuff in R, and it's sort of like a race to the end. It gets pretty intense, and there's not a lot of like breaks anymore. We do have a little bit of a break for the data collection activity. I'll post a video for that in the next couple days so that you understand how to do that activity. But the literature review and the midterm exam, most of you did a really good job, so you should be proud of yourselves. And put all that aside because we're not going to do anything else with that for the rest of the semester. So for today, you're going to need this R file, and you'll need, sorry, I'm going to do the annotate thing so that you can see my mouse. I might do, yeah. So you're going to need the ztest.r file. You're going to need the SAT, CSV, and the GRE. These are two data sets that I made up, but it's okay. They'll work for our purposes. Let me show you how to find them. Hopefully these will get a little bit easier to you of how to do it, but if you go to modules, and then you go to the one that we're on, so this would be week 7. Here we have the z-test. There's a quiz you'll take. Here are the lecture slides that we're using, and then right here is the R code. This is a data set, and that is a data set. This is your homework. So I'll just click on those. And then if I click on that, it will download that file. And then if I go next, and I click on that, it'll download that file. If I go next, and I click on that, it'll download that file. It looks like the, oh yeah, the R code open too. So if it works right, you have this code here that shows you how to do the z-test stuff we're going to do in class. The data sets, you'll want to open them in R. You don't want to open them in any other way. Okay, so let's talk about hypothesis testing. Hypothesis testing, inferential statistics, deals with probabilities. You're never going to be 100% certain of things. If we knew something with 100% certainty, there's no reason to use statistics. Statistics is all about the probability of something occurring. So we want to eliminate competing explanations, but we also recognize that there's some uncertainty, that sometimes our predictions are going to be wrong. So this 2x2 table kind of gives you a sense of the different options you can choose. These are selections you make, and I ask you in assignments, what is your alpha? So your alpha is something that you choose, and it's represented in this table too. Alpha is the probability that you're going to reject a null hypothesis that is really true. In inferential statistics, we never show that we're right. We show that the null hypothesis is unlikely. The null hypothesis is that there's no relationship, or that there's nothing there. If we demonstrate that the probability of there being nothing there is small, then we conclude that we must be correct. That's the foundation, that's the logic behind inferential statistics. So you might say, well, then I'm going to make this really low. I'm going to set this at 0.00001, right? You might choose that. That's actually exactly what happens in genetics, because there's billions of observations in the genome when you're doing genetic analyses. And so they do set their alpha really, really low. But the lower you set your alpha, the more you increase your beta. So this is the opposite of alpha. So the lower I set my alpha, the higher my beta becomes. So alpha is the probability of a type 1 error. Beta is the probability of a type 2 error. A type 2 error is you accept a null that's really false. We call these false positives. The reason that in cancer screenings you'll often get false positives is because, again, they set their test so low because they want to have precision. They set their type 1 error rate very, very low, which means you get a high false positive rate. In physics and the natural sciences, they typically choose an alpha of 0.01 because things in physics tend to be constant. When Newton estimated the rate of gravity 500 years ago, it's remained basically the same. The rate of gravity, gravitational pull on the Earth, has not changed since 1500. But in our world of social sciences, there are a lot more change. It's a lot more dynamic. There have been very many changes to systems of government since 1500. And even if you want to say, well, Britain's still around and the monarchy's still around, it's not the same form of government now that it was then. So because in the natural sciences, things tend not to change as much, they set their alpha a little bit lower. In social sciences, we set our alpha, or the probability of a type 1 error, at 0.05. So that's what this table is trying to help you understand. So typically, alpha is set between those numbers. And then when you report it, we say our P is less than 0.05, right? That means that if the probability of the null being true is less than 0.05, then we would reject the null hypothesis. Okay, so how does inferential statistic work? You take a representative sample of the population. Then you give them some kind of test. And then you have to compute the mean, right? Because the central limit theorem talks about that if that sample is binomial, well, you can't assume normality. But the means of those samples are normally distributed. So you get like a mean or a correlation or something like that. And then you decide, is it statistically significant? Is it anything? And then based on the results of that sample, you make an inference about the population. So if you find that the probability of you getting a sample with a mean score of whatever you get is very unlikely if there was no relationship, then you assume, oh, there must be something happening in the population. That's the logic behind inferential statistics. If you think about it long enough, which for most of you, this is the first time it's really been introduced to you. So it's not sinking in for you quite at the moment. But as you sort of like contemplate like what this means, you will have way less confidence in the significance of things that people talk about in terms of science. So let's say you have a normal distribution. 95% of everything is going to be in this region here. 5% of the values will kind of fall in this range, which would be about 2 standard deviations above the mean. So if I take a sample and I get a score in this range, it's unlikely for me to do that and have this null hypothesis be the way things really are. If the way things are the way everyone assumes them to be, I should have my sample mean somewhere in this range. So if I get a sample mean out here, it means that this distribution probably doesn't represent reality. So we reject the null hypothesis of whatever the opposite of whatever we think. We say this isn't true, ours must be true. You could also do, right? So if you do a one-tailed test and you say, I think if you say my hypothesis in my z-test is a greater than, then you would just reject in this region, and then your z-score would be 1.64. Or you could do less than, and then it would be in this region, it would be negative 1.64. But a value up here wouldn't matter because you chose this as your hypothesis. So most often what we do is we choose something where it's both sides, or we say not equal to, in which case 1.96 becomes the critical value, plus or minus 1.96. So if I do a test, a z-test, and I get a test statistic that's somewhere between negative 1.96 and positive 1.96, if I get something in this region, I'm going to not reject the null hypothesis. I will fail to reject it, or I will accept the null. But if I get a z that's less than negative 1.96, or greater than positive 1.96, I will reject the null hypothesis. So that's the idea. So you use a z-test when you want to examine the difference between your sample and the population. So let's say that this is the population distribution for SAT test scores. And let's say that I have a sample of people that are taking the SAT test. And I want to know, do people in my sample score significantly better than people in the population who take the SAT? I could do a z-test. I convert it to a z-score, right? So what I do is I have my students take the SAT test. I take the mean of that group of students that took the test. I convert it into a z-score. And if it's up here, if my z is bigger than 1.96, I say people in my class are significantly better than the population at the SAT test. And if it's down here, I'd say people in my class are significantly worse than the population at the SAT test. That's the idea. You cannot do a z-test unless you know the population mean and standard deviation. Otherwise, you can't do this test. So that's one clue for you if you're trying to figure out how do I know if I'm going to use a z-test? Well, I would have to tell you the population mean and standard deviation. Also in the book, there's this little tree diagram that we'll use for all of the various tests we use. And you can just, are you examining the difference between one sample and a population? If yes, you use a one sample z-test. Here's how you compute the z. You take the mean of your sample, subtract from that the mean of the population, and divide that by the standard error of the mean. The standard error of the mean is this population standard deviation divided by the square root of the sample size. Don't worry, you don't have to do this by hand. We can do it in R. So let's say that the population for the SAT, let's say the mean score is 500 with a standard deviation of 100. My class of 135 people, let's say they had a mean of 490 and a standard deviation of 98.78. And I want to know, did my class do better than everybody else? Now, you could be in kindergarten and look at this and say, no, 490 is less than 500. Yeah, that's right. So oftentimes in inferential statistics, this is one of the weird times, right? Because we happen to know the population mean. So you could just look at it and see that they're not the same. But we want to know statistically, are they statistically different from each other? So that's why we would do a z-test. We want to be able to say significant or put a star by it or something like that. In my view, and what I often tell people who don't understand statistics is, why are you doing a stupid statistical test? Just show us and we can look at the means and we can see the difference on our own. You don't have to do a t-test or a z-test or whatever to show us that they're different significantly. So the null hypothesis is that my sample mean equals the population mean, or 490 equals 500. I know it sounds stupid. Guess what? Almost all null hypotheses are stupid. The alternative hypothesis is that those two don't equal each other, or that this does not equal this. I choose my level of risk, or the type 1 error, which is 0.05 based on our discussion previously. The appropriate test statistic is the z-test. So then I'm going to compute my z in a second. I'll show you how to do that. And then I'm going to look up the critical value of the z-test. So I'm going to two-tail test. So I'm going to go 0.025, and my critical value is 1.96. Then I'm going to compare my z to 1.96. And if my z is, we'll just do this picture again. If I get a z out here or out here, I will reject the null hypothesis. But if my z is in between these two, then I will not reject the null. So how do you do it in R? I'll show you. Let's do the SAT data set. So first I got to read in my file. And I had these in downloads. So I'm going to do the SAT. So there's my data set, 130 5 observations of one variable. Let's just look at the mean. I call it the wrong name. So the mean of mine is actually 400. I know in the slides I say that the mean is 490. My mean's actually 400. Okay, so you need to use this package called Basic BSDA. So how do you get that? You go over here to Packages, you go Install BSDA, Basic Statistics and Data Analysis. You just click Install, it'll install it for you. Then you need to load in the package. So you either have to check on that box or you have to run this thing that says library, BSDA. Then, once you've done all that, it'll work just fine. So here's how it works, right? z.test is the function. I tell it my x variable, $D1 $SAT. Y is null because I don't have a Y. I give it the population mean, which is 500. I tell it the population standard deviation, which is 100. And then this confidence level I can leave on or take off. Let's just see with this. Run that code. I think I could actually change some. I can take this confidence level off because that doesn't matter that much and get the same answer. It doesn't even change anything at all. And I think I could even get rid of this Y. Yeah, you don't even have to put the Y in. You'll get all the same answers. Now, some people on this p-value, they say, I don't like that. That's scientific notation. So 2.2 times e to the negative 16 means you take that decimal and you move it 16 places this way. So you can do this thing called options, and then scipen equals 16. And then if I run that again, now I get my p-value like that, right? Some people like that better. So here's my z, negative 11.34. If I go back to here, negative 11.34 is, this is negative 3, all the way, way out there, right? So far out. So that is in this region where I would reject the null hypothesis. The other thing I could look at is I could see that my p-value is less than 0.05. The p-value is the probability that the null is true. The probability that the null is true is less than 0.05. That was the alpha that I chose. So I would reject the null hypothesis based on that. And that's how you do a z-test. You just calculate it, compare your critical value to the value that you get in your test statistic, or look at the p-value, and based on that, you can tell reject, not reject. Okay, so then now it's time for you to practice. Go ahead and pause, see if you can do this. Right, here's all the information you need to calculate that z-test, but then here's some code for you, right? So you can read in the data set like that. It's the GRE data set, 250 observations of 2 variables. Sorry. Here's the code that runs that for you. Again, if it were me, I would just get rid of this stuff that you don't really need. You could do just like that, right? If you run that, you get your answer. So go ahead and run those and then pause. I'll run through the rest of these slides rather quickly because you can pause and stop it on your own, and I don't want people to wait longer than they need to. So what is your null hypothesis? So just make sure that you consider these on your own and don't just look at the answers that I tell you. Right, so the null hypothesis is that your sample mean equals the population mean for that variable. The alternative, that they don't equal each other. What test will you use? What is the critical value? Plus or minus 1.96. What is the value of your test statistic? Right there is where you get that answer. Based on that, what do you do with the null hypothesis? You, well, reject, right? You reject the null. This is bigger than 1.96. Okay, we'll try it again. Now we'll do it with the verbal scores, right? This is actually true about the GRE. So we want to know, is your verbal score significantly better? In this case, I would say yes. People who took my class did significantly better on quantitative reasoning than everybody else. Now we're going to go verbal. Again, if it were me, I would change the code to things, get rid of things you don't need. Oops. Then run that. Okay. What is your null? Pause it until you're ready to go. Sample mean equals population mean. What is your alternative? Sample mean does not equal population mean. What test will you use? What's the critical value? It's going to be the same critical value. What's the value of your test statistic? And so based on that, you reject the null. So when we're in class doing this, typically people are super bored and upset by this point, and so we try and have a little bit of fun, but can't do that with you in the online version. Sorry, you just have to miss out on a lot of fun that we would have if we were taking this in person. Oh well. Don't intentionally fail the class just so you can take it face to face with me in a future semester. It's better to pass the class and move on. We can have fun in other classes. So the z-test is the simplest of all the inferential statistics tests. It's easy to do. The whole purpose is to like get you started in how inferential statistics work. So we're going to slowly build on this, right? The overall method that we use for the z-test is the same as all the other tests. We go through the same steps. All we do is change how we calculate our tests based on our question and what our sample looks like. So make sure that you're familiar with this and that you're comfortable with it. And again, as soon as you're done watching the video, I recommend do the homework because that's the best time to do it. Okay.